The interstellar object 3I/Atlas presents a remarkable and intriguing case that continues to challenge conventional understanding of cometary physics, especially in light of the most recent observations that contradict expectations for a natural comet undergoing intense solar heating. Despite earlier predictions that the object might fragment or disperse due to powerful jet activity observed in previous months, new high-resolution images taken on November 11, 2025, by astronomers David Jewett and Jane Liu using the 256-meter Nordic optical telescope at La Palma demonstrate conclusively that 3I/Atlas remains a single, intact body with no evidence of breakup following its perihelion passage 2 weeks earlier. These images reveal a prominent elongation in the coma of the object, the glow of dust and gas surrounding it, projecting at a position angle of approximately 106 degrees with an uncertainty of about 10 degrees. Interestingly, this aligns closely with the projected sunward direction at 115 degrees, implying that the activity producing this structure is directly influenced by solar radiation pressure and the geometry of the object's orbit at the time of observation. This feature strongly resembles the anti-sunward tail structure observed by the Hubble Space Telescope on July 21, 2025, which showed an unusual anti-tail pointing toward the Sun, a phenomenon rarely observed in typical comets because anti-tails require specific geometries and dust release conditions to become visible. The new image also reveals a secondary, weaker asymmetry at a position angle of approximately 301 degrees, closely aligned with the projected anti-solar direction at 295 degrees, suggesting that dust and gas continue to flow both toward and away from the Sun in a pattern distinct from conventional cometary tail behavior governed by solar wind and radiation pressure. In astronomical units, the distance between 3I/Atlas and the Sun during these observations was about 1.43 Australian dollars, while the distance from Earth was approximately 2.16 Australian dollars, making the imaged region, which spans roughly 500,000 kilometers, large enough to capture significant structural features and dust distributions around the object. Notably, the long-range jet structures that were clearly visible in wide-field photographs taken only days earlier, stretching up to 1 million kilometers on one side and nearly 3 million kilometers on the other, are not evident in this dataset. This discrepancy is likely due to the use of an R-band optical filter in the recent observations, which suppresses most gaseous emission lines and therefore reduces the visibility of gas-dominated jets, leaving only dust-scattering features detectable. However, even with these instrumental constraints, the persistence of clear structural asymmetries and the continued integrity of the nucleus stand in sharp contrast to what one would expect from a natural comet producing such enormous jets. The scale of the previously reported jets is extraordinary, and their existence raises serious questions about the physical behavior of 3I/Atlas. Based on typical cometary physics, a natural comet at this distance from the Sun should exhibit gas outflow velocities around 0 kilometers per second, consistent with the local sound speed of sublimating volatiles, such as CO2 or H2O ice. If the jets extended to 1 or 3 million kilometers, then, given this velocity, they must have persisted for periods ranging from 1 to 3 months. Moreover, the observation that the Sun-facing jets were halted by solar wind pressure at around 1 million kilometers implies extremely high mass densities within the jets. Calculations based on the solar wind's ability to counteract this flow suggest mass densities of several million proton masses per cubic centimeter at that distance, astonishingly high compared to densities observed in typical cometary comae. When this density is multiplied by the estimated outflow speed, the implied mass flux becomes enormous, on the order of 5 billion tons per month per million kilometer wide section of the jet. Such a massive and continuous outflow of material would require a tremendous source of energy. If the jets consisted primarily of carbon dioxide gas, then sublimating 5 billion tons of CO2 over roughly a month would require at least 3 times 10 superscript 1 joules of energy. At the perihelion distance of 3I/Atlas, the Sun provides approximately 700 joules per square meter per second. To accumulate the required energy, the absorbing surface area would need to exceed 1,600 square kilometers, which corresponds to a spherical body approximately 23 kilometers in diameter. However, imaging data from the Hubble Space Telescope place an upper limit of only 5.6 kilometers on the diameter of the nucleus, meaning that the required surface area is about 4 times larger than the entirety of the object itself. If the jets were powered by sublimation of water ice rather than carbon dioxide, the required diameter would be even more extreme, around 51 kilometers, because water ice requires substantially more energy per gram to sublimate. Furthermore, on natural cometary nuclei, volatile ice tends to be patchy and only exposed across relatively small portions of the surface, reducing the effective sublimation area even further and making the energy requirements even more unrealistic. These combined discrepancies strain the limits of traditional cometary models and make it increasingly difficult to explain 3I/Atlas using familiar solar system analogs. The persistence of 3I/Atlas as a single, coherent body despite evidence of mass loss on a scale far beyond typical cometary activity introduces yet another anomaly that cannot be reconciled easily with standard theories. Instead of breaking apart under the extreme outgassing forces, as natural comets typically do under much milder conditions, 3I/Atlas appears remarkably resilient. The contrast between the immense jets inferred from earlier images and the current structural integrity of the nucleus raises questions about the internal composition, mechanical strength, and energy processing mechanisms of the object. If the jets truly persisted at the scale reported, then either the object must possess an internal reservoir of volatiles far exceeding its size, an implausibly large energy absorption cross-section, or an entirely different mechanism, one not based on sublimation, must be responsible for the observed jets. Traditional comet models simply cannot accommodate these extreme quantities of mass loss without catastrophic fragmentation. The situation is made even more complex by the asymmetrical jets and tail features that appear to shift in orientation, yet do not correlate with expected solar-driven outgassing behavior. The presence of an anti-tail pointing toward the sun, for instance, is itself unusual and typically indicates the presence of large dust particles following gravitational rather than radiation pressure trajectories. However, the overall brightness, scale, and persistence of these structures in 3I/Atlas exceed normal ranges by significant margins. If one attempts to force a conventional comet model to fit the data, the inconsistencies multiply rather than resolve. The energy budget does not balance. The physical strength of the nucleus appears improbably high. The mass loss rates are incompatible with the observed size, and the geometrical formation of the jets lacks a coherent, sublimation-driven explanation. These accumulating anomalies highlight why 3I/Atlas cannot simply be swept under the rug of traditional cometary knowledge, as some may wish to do in order to maintain a simplified or comfortable narrative about interstellar objects. The scientific method demands that we confront contradictions rather than ignore them. When an interstellar object behaves in ways fundamentally inconsistent with known natural processes, the responsible course of action is to broaden the investigative framework rather than narrowing it. As Albert Einstein famously said, knowledge is realizing that the street is one way. Wisdom is looking in both directions anyway. In the case of 3I/Atlas, wisdom requires that we consider possibilities outside the standard comet model, remain open to unconventional explanations, and acknowledge that this object may represent a category of interstellar material with properties not yet understood. Whether this ultimately points to exotic compositions, unfamiliar physical processes, or entirely new classes of objects traversing interstellar space, the anomalies presented by 3I/Atlas deserve careful, unbiased scrutiny rather than dismissal. Until the energy budget, jet mechanics, structural resilience, and observational inconsistencies can be explained in a self-consistent manner, 3I/Atlas will remain one of the most mysterious and scientifically provocative interstellar visitors ever observed.